Okay, let's look at two gears. And our first gear is going to be gear A, and it's going to be sort of a small gear. And our second gear is going to be gear B, and it's going to be a larger gear. So the radius of B, so R of B, is going to be 0.15 meters, and our radius of A is going to be 0.05 meters. Now we're going to say A has some angular velocity, and this angular velocity is going to be 20 radians per second, and it has an angular acceleration, which we'll define in a minute. And what we're interested in is figuring out what this angular velocity of B is. So we want to figure this out. And I want to do this problem in two ways. The first way is when my angular acceleration of A is a function of the angular position, so it's a function of theta. And this is going to be equal to 0.25 theta cubed plus 0.5 radians per second. And I'm interested in finding this after A has made 10 revolutions. And the second way I want to do this is when theta, the angular acceleration of A, is a function of time, and it's equal to 4t cubed radians per second. And this, I want to figure it out after 2 seconds have passed. Okay, so this is going to be the two ways that we're solving this equation, or we're going to solve this problem in these two different ways. So our first way, when our angular acceleration A is a function of this position, this theta, and it's equal to this expression, we know that since it's a function of this angular position, we cannot use our kinematic equations that we have for rotation about a fixed axis. We're going to have to go about a different way of doing this, and we're going to have to integrate. So we have this alternate expression. We have that the angular acceleration is equal to the angular velocity times the derivative of the angular velocity with respect to angular position. So we can use this equation because this d theta right here is what this angular acceleration is a function of. So if we substitute in our expression for our angular acceleration right here, we get 0.25 theta cubed plus 0.5 is equal to omega times d omega over d theta. Now, what we have to do now is separate our variables and integrate. So we're going to move this d theta to the other side of the equation, and we're going to get 0.25 times theta cubed plus 0.5, and this entire side of the equation is going to be multiplied by d theta now, and this is equal to omega times d omega. And we want to just figure out what our bounds for all parts of this equation are. Well, we don't know what our final velocity of angular velocity of A is. We're not sure. We know that we have an initial angular velocity of A, which is 20 radians per second. So we're going to integrate from a final unknown angular velocity from the initial angular velocity, which is 20 radians per second. We know that its final angular velocity is not going to be 20 because it has some sort of angular acceleration. So since we say it starts at 20 radians per second, we know it has to be faster or slower depending on whatever this quantity turns out to be. And what's going to be our bounds for this integral right here? Well, we want to know what this is after 10 revolutions this gear has made 10 revolutions. So in order to convert to radians, because this is what we need over here, we have to say that 10 revolutions is going to be multiplied by 2 pi radians, because that's what 1 revolution is equal to. So these units cancel out, and we get this is equal to 20 pi. So we're going to integrate from 20 pi from 0, because we start at 0 and we move 10 revolutions. And now we just have to evaluate this integral. Well, with this integral, it's going to be 0.25 theta to the 4th over 4 plus 0.5 theta, which is evaluated from 20 pi to 0. And this is going to be equal to omega squared over 2, evaluated from a final angular velocity from the initial angular velocity, which is 20. Now, if we evaluate our bounds, we're going to get this number here, 974,091 plus 31.4 is equal to omega a squared over 2 minus 200. And we can solve this equation out for omega a, and we get a final angular velocity of a, which is equal to 1,396.4 radians per second. Okay, so that's what this final angular velocity of a is. So what's the final angular velocity of b? Well, we know that these gears, they touch right here, so we're going to say that the angular velocity of b at this point, we're going to say the velocity of b at this point is equal to the velocity of a. So the velocity, since they're touching, the velocities have to be the same. So what a gear is essentially a rotation about a fixed axis. The gear is rotating about its center. Both of these gears are rotating about their center, and we know the equation we have for rotation about a fixed axis is the velocity is equal to the angular velocity times r, and r is the distance the point we are looking at is from the fixed axis that it is rotating around. And in this case, it's just the radius of the gear. So what we can say is that the velocity of a is equal to our velocity of gear b. So our angular velocity of a times our radius of a is going to be equal to our angular velocity of b times our radius of b. Now, we plug in our information. We know that this angular velocity of a, we just found it. It's 1,396.4. Our radius of a is 0.05 meters. And this is equal to omega b, which is what we're looking for, times our radius of b, which is 0.15 meters. And we can solve this right here, and we can get the angular velocity of b is going to be equal to 465 radians per second. So this is the answer to the first part of the problem. Now, what do we do if this wasn't our angular acceleration and this was our angular acceleration? Well, if our angular acceleration is equal to 4t cubed, this means our angular acceleration is a function of time. So instead of using this expression for our angular acceleration, we need to just pick another one. So the one we're going to pick is our angular acceleration is equal to the derivative of our angular velocity with respect to time. And we want to, again, sub in this 4t cubed to this side of the equation. So we get 4t cubed is equal to the derivative of our angular velocity with respect to time. Now again, we're going to bring this dt over to the other side, and we're going to integrate both sides. Separate and integrate. So we get 4t cubed dt is equal to d omega. And what are our bounds? Well, we want to go from 2 seconds, so our final time is going to be 2. Our initial time is going to be 0. Our final angular velocity is going to be unknown. We're solving for it. And our initial angular velocity, again, is going to be this 20 radians per second. So from here, we're going to evaluate this integral. We're going to get 4t to the 4th over 4. This is going to cancel out, so we get t to the 4th, which is evaluated from 2 to 0. And this is equal to omega, which is evaluated from WA to 20. Now, if we plug in our bounds, we get 2 to the 4th. So 16 is equal to omega A minus 20. And we get a final angular acceleration of A, which is equal to 36 radians per second. Okay, so we're gonna use the same logic, which is right here, about the velocities. Our velocity of A is equal to our velocity of B. So omega A times the radius of A is equal to omega B times the radius of B. Omega A is 36. Our radius is 0.05, or 0.05. We don't know what this angular acceleration of B is, so we're going to leave it as omega B times this radius of B, which is 0.15. And we're going to solve for omega B. And when we solve, we're going to get this is equal to 12 radians per second. And this is our final answer for the second way to do this problem.